Alrighty, welcome to 10.3 Rules for Logs. The spacing of this is a little off, so I apologize, but your notes should be fine. Should all be on one concise page, and it really doesn't matter. So, in previous videos we've talked about logarithms, how they are inverses of exponentials, right? How they can be rewritten as an exponential, how they can be graphed, things of that nature. Today we're going to talk about, or in this video I should say, we're going to talk about the rules for logs. Way back in chapter 5, we had rules for exponents. Seeing as how logs are the inverses of exponents, it makes sense that there are also rules for logs. And you'll be surprised how similar they actually are. The first table you see here, it's actually split into two tables, my apologies, is actually the exact same table that was used in Unit 5. It's all your exponent rules, your product rule, your quotient rule, your zero exponent rule, your negative exponent rule, your distribution rule, power over power, all those things that you know and love from exponents. Logarithms, once again, since they are exponents, have their own set of rules, but they're actually the same rules. They're just in a different format. Okay, so we're really not learning anything new. We're learning something in a different form. That's what we're doing. So as you see, there is a product rule, a quotient rule, a power rule, a zero rule, and a negative exponent rule. The only thing that there isn't is a distribution rule. For that, it just makes more sense to convert it back to an exponent and deal with it then. Mostly because you really don't change bases for logs, right? A lot of the other exponent rules you don't change base either, but that one you kind of do, so here we're just not going to have one. Let's go rule by rule. First one is the product rule. It says if you have the log of something, remember these are all just variables, so whatever base you have, whether a is 2, 3, 4, 5, 1/2, 1/3, whatever you want, right? As long as you have that same base, if you have x times y or something like log 2x, well then you can break it apart, right? You can break it apart into log of one plus the log of the other. So the product rule says if you have two things being multiplied in that middle part, you can kind of expand it out by adding instead of multiplying. For example, if you have log 2 8, right, since 8 is 2 times 4, you can split that up into log 2 of 4 plus log 2 of 2. Notice they each get log 2. The base doesn't change. That a never changes. It always stays the same. And then you can also go backwards. So if you had the right side, log 2 of 4, and you suddenly needed to add log 2 of 2, well then that squishes together into log 2 of 8. You have to be very careful though. It does not expand by adding, okay? When you start adding, you don't add like terms, quote unquote. You combine them using the product rule. So log 2 4 plus log 2 4 is not log 2 8, it's log 2 16, right? Another thing I see often is if we had the other one, the example here, people accidentally may think this is log 2 6, and that is not true. You have to multiply them together. Okay, so addition, a product rule is adding when you multiply, if that made sense. Similarly, we have the quotient rule, right? If you have x divided by a, you subtract them. It's almost exactly the same format as product rule. It's just instead of multiplication and addition, you now have division and subtraction. For example, if you have log 3 of 24, sometimes, if you want to be super clear, you can put parentheses around that. You get log 3 of 24 is log 3 of 8 minus log 3 of 3. So notice once again, it's not 8 minus 3. This doesn't end up equaling 5. You have to actually divide them. So 24 is 8 divided by 3. So I can split up these logs with a subtraction sign. It is not, once again, an actual subtraction. It is not 12 and 12, or it's not 36 minus 12, right? It's nothing split up like that. You don't split it up by addition or subtraction. You split it up by multiplication and division. Cool. Those are the two first most important. Another really important one is the power rule. So this one happens more often than you think, where you get powers within powers within powers. For example, so you have log of something, log something of x to the y, right? That additional power you see in there, because on the outside is an additional factor. So it goes kind of like a coefficient. Actually, it is a coefficient. For example, if you had log 3 of 16, well, 16 is 4 squared, right? So you have that extra square in there. You can take that out and knock it down a peg by doing 2 times the log 3 of 4. Notice once again, the base does not change. It's still log 3, right? But it's just kind of been knocked down a peg, kind of like, oh, you've got 2 in there, let's take 1 out, right? What it is not is it's not multiplication. So it's not 2 times 8, all of a sudden 8 goes on the outside, right? It's in this case, log 16 would be 2 to the 4th power, so it'd be 4 on the outside, not 8 on the outside. All right. Log 0 power rule, once again, anything to the 0 power is 1. So if you were to rewrite this, right, if we rewrote this using our circle, we would see a to the 0 equals 1, which makes sense. That's just the 0 power rule. So this one's kind of on the nose, right? 2 to the 0 is equal to 1. And once again, remember, nothing to the 0 power is equal to 0, right? It's not multiplication, it's an exponent. It's anything to the 0 power is equal to 1. Reverse log power, if you have 1 over x equals negative y. My apologies. Yeah, so that's just negative power. You can change, you can put negatives wherever you want. Fractions end up equaling negatives. Because remember, the negative exponent rule, right? If you have a negative exponent, if we were to rewrite this, you get a to the negative y equals 1 over x. And that makes sense, right? Because any negative power is going to give you a fraction, right? So this is, again, this one's just sort of derivative. Well, they're all really sort of derivative of the exponent rules, but these last 2 are kind of like, well, yeah, duh, whatever. The first 3 are the main big ones, the ones that we're really going to be breaking, and we're going to be expanding and combining logarithm expressions with. Okay, so those first 3 are the ones you want to commit to memory. Alrighty. Let's get started with some examples, kind of see these guys in action. So here we have example number 1. Simplify the following logarithmic expressions. For these ones, we're going to be using power rule. Or sorry, quotient rule, product rule. Let's go through all of them, okay, before we pick the right one. Haha. Power rule. How do I know that? I know that because I see a lot of addition, right? Addition means power rule. So we're going to combine these. We're going to simplify it so you don't have so much going on. You're going to find it super easy. So as we've seen with all these rules, the log and the base part are all going to stay the same. So this is going to be log still 3. But now I have 6 and 12. Log 3, 12 plus log 3, 6. So I'm going to get log 3, 18, right? No, I'm going to get 12 times 6. 12 times 6. So in reality, we have log base 3 of 72. That would be our simplification. I always normally kind of put parentheses around 2-digit numbers. That is not necessarily a requirement. Totally yours to choose. But that's it. That's product rule. So let's try another one. We have log 6x plus log 6, 4. So once again, we see log 6. That's not going to change, right? It's not going to change. This time we have x times 4. Not x plus 4, x times 4. It's plus in the expanded version. If you want a plus sign, you need 2 logarithmic words. You need 2 logs in the expression. For one of them, you need to multiply. So this combines to log 6 4x. Once again, you can put little parentheses if you want. That tells the audience, yes, the x is actually in the logarithm, not being multiplied by it. That's probably really clear and much better than just leaving the parentheses off. But again, that's a choice of yours. All right, moving on to C. Here we have log x 12 plus log x 15. Can I actually combine these? Well, yes, even though you don't know the base. Remember, variables in one expression all represent the same number. So if x was 2, if x was 5, if x was 6, well, I would plug it into both occurrences. So no matter what, this log is going to be the same. So this is log x still. So we can do that. It's legal because it's the same variable. If it was log x 12 plus log y 15, no, that wouldn't work. That wouldn't apply. Those would not be the same, right? Because I'd have to make sure that I have to plug in the same number for both x and y. But here they're both x, so no big deal. Excuse me. And then we do 12 times 15, which is, I believe, yep, 180. 180, because it'd be 120 plus 60, which would be 180, yeah. There we go. Alright, last but not least, kind of like I said before with the x and the y thing, they have to be the same base, right? They have to be the same base. I could definitely try and say, yeah, I can consolidate these, that would be 2 times 4 is 8, and then what do I put in the subscript? What do I put for the log base? That doesn't make any sense to me, right? Do I put 6? Do I do 2 plus 3? Is that 5? Do I just do 23? What do I do? Do I pick my favorite one? If you have to ask, it's wrong. If you have to ask, then it's not possible. This is actually the simplified form. Okay, less work for you. Oh well. Okay, cool. So we can maybe just write simplified. Simplified. Alright. That's product rule. Pretty on the nose, right? Let's try quotient rule now. We're going to kind of do it backwards. This time we're going to expand instead of contracting or condensing, sticking together, right? Here, all of these guys were apart. Now we're apart and we wanted to put them into one. Now we're going to do the other, we're going to go backwards with the quotient rule. The quotient rule is so like the product rule that we can do that. So we're going to start that here. Let's start breaking them apart. So if I want to break this apart, I have 7/9, right? Instead of dealing with 7/9, log 4 of 7/9, why don't I just break this into 2 of the same base, log 4, and then 7 and 9 instead of 7/9. Because that's a quotient, right? 7/9 is 7 divided by 9. But what do I stick in the middle? Do I stick a big old division sign? No. Very similar to the product rule, I stick a subtraction. And that's just their expansion. Why we would need to use that? Maybe we'll use it in our simplification with bigger ones, right? Maybe if I see, I don't know, something I can cancel with a log 4 of 7 instead of log 4 7/9, or maybe I could figure that out in a calculator easier. We'll see how to do that later. Those might be helpful, right? So we'd want to expand. Sometimes it actually helps us solve more than if we keep it condensed. Let's try another one of those, actually, before we go on to an actual condensing one. Let's do another one of these. So I have log 3 of 27, 27, goodness gracious. Okay, hold on. Start all the way back at the beginning. Let's go back to where we were before. So I have log 3 of 27 over 5, right? And sometimes these aren't written as fractions. Sometimes they're written as 25, and you can break it into 5 and 5, or they're written as, I don't know, 30, and you can break it into 6 and 5, right? So 30 divided by 5, yeah, you can break it like that. You can break it up. You might want to use product rule in those cases, but there's cases where you use one and the other. Here, though, pretty easy and on the nose. You got log. I'm just going to zoom in because it's much easier to write that way. I'm just going to try not to tap the screen. So you get log 3 of 27 minus log 3 of 5. Not divided by, not plus, not multiply, not to the power of subtraction, right? Many of you are going to like the quotient rule because it means you don't have to deal with fractions, and I know how much you guys love fractions, so I'm sorry to disappoint you, but you can get rid of them. Okay. Let's try condensing now, right? So let's condense these. Let's see if we can do that. We've got log 5, 6 minus log 5x, right? Can I use the quotient rule? Yes, I can, because of 2 reasons. One, it is the same base, the same 5, right? And it is also subtraction. So I can definitely condense these into 2. I'll make one. I'm sorry. That's so frustrating. Okay, let's just go there, I guess. So my hand likes to sit right where that little magnifying glass thing is in the corner, so it keeps, yeah, anyway. Okay, so log 5, make one of them instead of 2, but this time in the parentheses, it's not going to be 6 times x, it's going to be 6 divided by x, and that can actually change a lot of things, so you want to be super careful about which one goes with which, right? I don't know about you, but I always kind of think addition and multiplication go together. Kind of think of those as kind of the light side, and then you've got addition and or subtraction and division, kind of like the dark side. I know that's super Star Wars reference, but that's always how I've kind of pictured it. The subtraction and division always have so many more rules with them, so they're kind of like the dark side that go together. Then the light side, multiplication and addition, they're always nice and easy. Anyway, that's what I like to think of. So they kind of pair up naturally for me. They don't pair up naturally for you. I hope that kind of helps. Alright, and the last one. Can I actually combine these? I can't, right? And here's the problem. Why? Yes, they're being subtracted, but they don't have the same base. Once again, if I tried to do that, if I actually tried to write this together, 4 divided by 3, what am I supposed to stick in the logarithm? Again, if you have to ask, you don't, right? If you have to ask and you can't come up with an answer, then you're probably not doing it right. So we're not going to do that. We're just going to keep this as it is. There is no way to simplify that using the product rule. Maybe there's a way to simplify it, but there's not a way to simplify using the... Okay, let's move on to the product rule now. I'm sorry, not the product rule, the power of a power rule. Some people like to say power rule, others like to say power of a power rule. I'm kind of the latter group because I like to draw reference to the exponent rules. Right in there, it's called power of a power. Technically, there are not two powers here, right? But if you look hard enough, a logarithm is sort of the inverse of an exponent, so yeah, there's a whole argument there. But whatever you want to call it, it has to deal with exponents, right? It has to deal with powers within the logarithm. So we see here log 5 of 4 squared. Now I could write this as log 5 16. That's one way to simplify it. Wouldn't technically be wrong, but if I'm trying to reduce it, right, later on if I see another log 5 of 12, right, well then I can reduce it and use that instead of making it 16. I can use something and, alright, anyway, I can make it simpler. It might be useful later on. So instead of just making the 16, I see the square here. The power rule says that's going to go on the outside. So we're just going to go ahead and put it on the outside as a coefficient instead of a power. And I know you guys love powers. They're super fun to deal with, but you know, you can get rid of them. Haha, just kidding. Yeah, so that takes it out. Pretty easy and on the nose, right? Don't have to worry about the same base, because there's no other logarithmic expression here. It's just the one, so this works for any base, doesn't matter. Like I just said, this works for any base, so in example B, we have log B of x to the 5th, right? So I don't know any of this. Is that going to cause a problem? Not really, because I still have the same situation. I have a logarithmic expression where the inside, the solution, is being raised to the 5th power. Because that is the case, I can take that 5 out as a coefficient. So I take the 5 out, everything else is left the same, except now x is not to the 5th power, it's just x. And maybe that's super helpful later on. Maybe we're going to find in the next section that some logarithms are really easy to calculate with your calculator. So maybe that one, whatever log bx ends up being, is super easy to calculate, and all I have to do now is times it by 5 instead of having to raise something to the 5th power and then solve for that. So that's where this can be useful. Alright, log 4 of 25. Well, this may not look like a power of a power rule, right? But there's a hidden exponent within there. Like I was saying before with the quotient rule, you can break things up. So here, instead of having 25, I know that's a perfect square. I can view this as log 4 of 5 squared. So if you see powers in there, you see stuff like 25, 169, right? Or some cubes, you can see like 81 is 3 to the 4th, right? And you can take that out. So you can rewrite them as powers, and then the power rule applies. You have log 4 of 5, right? So instead of log 4 of 5 squared, I have 2 times log 4 of 5. Alright, cool. Similarly here, 1/8 is actually a square, right? It's a square of, if we rewrite this, you can either do log 3 of 1/2 to the 3rd power, okay? Then we pull that out, we get 3 log 3 of 1/2. Totally legal. Maybe that's the move you want to do. But we also have the option that 1/2 is to the negative 1st power. It's 2 to the negative 1st power. So we could also say that this is 3, or we could just start from the beginning, we could say that this is also equal to log 3 of 2 to the negative third power, right? Not only do we get the 8 out, right, we also get the flip from the negative part. So we can also take out negative 3 log 3 to the second. Once again, whether or not you want to take that negative out depends on what you're doing, right? If you need whole numbers, maybe later on you have a product rule that you want to use 3 and 2 on rather than 1/2. That's up to you. You can take the negative out. But that's actually 2 rules in 1, which is pretty cool. So totally up to you. Technically, both of these answers are correct. Moving right along, we have log 2 of 2. Well, log 2 of 2 doesn't really do much, right? It has 2 is a prime number. You can't really take a power out of that one. Technically, you could take out a power of 1, right? You can take out a power there, but that doesn't really help you. So this would be simplified. Simplified, because it's prime, right? It's prime. Okay, over here, we have an example of the 0 power rule. Check this out. We've got log 178 is equal to 1. If we were to put, I'm going to use a different color. If we were to rewrite this as equals x, so log 178 of 1 equals x, then when we make our circle, 178 to the x equals 1. What's that going to be? What's the only power that brings everything back down to 1? That's 0. So this whole expression is just equal to 0. That means this whole expression has to be equal to 0. So the whole thing's actually solvable. I mean, all of these really you could solve. We're going to figure out ways to do that in the next section. But this one's so easy we can do it now if we just call it 0. That's our 0 power rule. So anytime you see a 1 in that argument, a lone singleton 1, it does not matter what the base is, it's going to end up being 0. So you want to hunt down for those 1s. If you see those, take care of them first. Just like anytime you'd see y to the 0, 2 to the 0 in an exponent rule kind of problem, here if you ever see a 1, take care of it first. It's equal to 0. Cut it out. You're done. Okay, cool. Alrighty. Let's start combining these together now. Let's see if we can kind of condense some ugly looking things into some prettier looking things and use maybe multiple rules at the same time. So in this first problem, we have log a of p minus log a of q plus 2 log a of r. Notice how there's a lot of log a. So I know I can do stuff here. It's still got to have that same base, right? It's kind of giving me a hint that the first thing I should focus on is definitely that parentheses, right? Parentheses in PEMDAS, always important. Super, it's the first one. Please, please, please excuse my dear Aunt Sally, right? What can I do there? That is straight up quotient rule. So first off, this is going to change to log a p over q, right? Quotient rule. So that's easy. That changes this right away. We've got log 2 log a of r left over. Well, I also see kind of a power rule on this second side. I can change that into not 2 times log AR, but I can move that back into the exponent, right? I can also undo this rule. So I have log a p over q plus log a r squared. So I can put that back in. And lastly, now I have an addition of 2 logs that have the same base, right? So I can multiply the arguments together, the inside. And I get log a of p over q times r squared. For simplification, you can also just put that r squared up top. Right, so it's the same thing whether you put it on times r squared or if you are an adult and want to simplify things so they're pretty, right? Take pretty things to your boss so they can actually pay you. Then you'd want to throw it up top, right? So this would be the simplification. Notice one argument. I don't have to hit log in my calculator 47 times. I can put in one thing for the middle and then take the log of that. So very simple, very easy to work with. Okay. Let's try another one. Let's go over here to get some numbers going. We have 3 log a to the 5th plus 1/2 log a to the 9th. Okay, good. More log A's. There's thing to be done here, right? I can start with a couple. I see a lot of coefficients, so let's start with power rule. Once again, just like the exponent rules, there is no set order to these. I don't know if that makes this harder or easier. It's really up to you. I think it makes it easier. If I don't, I can use anything I see, and it's not going to matter. That makes me kind of relieved, right? I don't have to be like, well, I didn't see the power rule, so the whole thing just fell apart, right? If you see it, use it, okay? If you see it, use it. There is no set order. There's no set order to these, and there's no set order to exponent rules. So I'm going to start with power rule, because I can choose, right? I'm going to start with this one becomes log A 5 to the third. Yes, I could simplify that. I don't think I'm going to at this point in time, because I want to see what's going to happen with the other stuff. Plus 1/2. Oh, I apologize. That's kind of the thing I'm taking care of. Log A 9 to the 1/2. Okay. We have this. Notice, now remember in our last problem where we had a negative exponent, right? It was not the case that I was taking out. It wasn't the case that this was the exponent, okay? It was not the factor in front. Notice these are positive, right? So I'm not changing it to a negative. It was, in fact, the argument that was the fraction. In this case, the coefficient was the fraction, so that fraction just goes straight up into the exponent, okay? If you recall, a fractional exponent means we now have the square root of 9. So maybe we can take care of that. But I think I'm going to finish with my product rules. I think I'm going to finish with my rules first. I'm sorry, my logarithm rules first before I go simplifying any numbers. Because I see two of the same base being added, and that means power rule. So we have log A of 5 to the third times 9 to the 1/2. Okay, well 9 to the 1/2 is 3, and 5/3 is 125. 125 times 3, that's 375. So once again, I have 125 times the square root of 9, which is 3, or log, I don't know why I changed that to 3 all of a sudden. Maybe I was just saying 3 so many times. I have log A of 375. If you have all numbers in that argument area, I think that's called the argument, then just roll with it, right? Simplify it. Nobody likes to look at 5/3 to the times 9 to the 1/2. Change it to 375. And you're done. Cool. Easy peasy. Once again, maybe you chose a different route. Maybe you put them together first and then took care of the product rule. And you can do that. You can definitely do that. You have to multiply all the coefficients and crap, but you could figure it out as long as you obey the laws of mathematics. When you have a coefficient on the outside, you'd have to multiply that like binomials, and it would be crazy complicated, but you could do it, okay? All right. Last but not least, the mega problem. Super fun. But notice it says 1/3 log bx plus, and I'm sorry I wrote over that, 2/3 log by minus 3/4 log bs minus 2/3 log bt. I see a lot of log b. It's definitely something we can all squish together, right? I see a lot of addition and subtraction, a lot of product and quotient rule. I'm going to have to be careful about which is which, right? I see a lot of exponents being represented as coefficients. I think I'm going to start there. I'm going to start with exponents represented as coefficients. I'm going to change this one to log bx to the 1/3 instead of 1/3 times log b to the x plus log b x, y to the 2/3 minus log b, what is it, s? Yep, s to the 3/4 minus log b t to the 2/3. Notice I'm not taking the minus part up into the exponent, right? I'm not changing that part. Is it illegal? No. I mean, you technically could. Of course, we saw in an earlier example, you can pull out a negative. It will probably end up in the same place, but for the first time doing this especially, or the second time, or if you're not very comfortable, I would just recommend keeping the exponent out. I wouldn't recommend putting it back in. If you see a way to take it out, I would go for it. If you see a way to put it back in, maybe it'll help you, maybe it won't. I don't know every problem in the universe, so maybe I can't say this like a blanket statement, but I would say maybe try keeping them out for the first couple times. All right, starting with this addition now, we could put those together. So we have log b of x to the 1/3 y to the 2/3. And then, you know what, I'm going to do a little bit of distribution here. I'm going to pull this out and make this minus log b of s to the 3/4 times t to the 2/3. See that? So I took out the minus and made it a product rule. See that? So it became minus this whole thing, which I should really put at other parentheses. Alright, so then last but not least, I'm going to try and write this as small as I can. This is a quotient rule, so I end up with log b, x and y on top, x to the 1/3, y to the 2/3, over s to the 3/4. Oh goodness, okay, that's not going to work. It's way too thick. Let me change my pen setting real fast. Change it to like microscopic. Okay. Alright, so then we have log b of x to the 1/3, y to the 2/3, over s to the 3/4, t to the 1/3. Now, even if you hadn't done that little maneuver of taking out the negative, you would have gotten the same thing, right? Because you would have had the first one being subtracted by the second one, so you would quotient once, and then you would do it again with the last one. So the two minuses, even becoming 1, you still have them both ending up on the bottom. So you still have this combined. Since it's all different variables, x, y, s, t, there's nothing within there that I can actually combine. So that is my final answer. Cool. So I hope these aren't looking super daunting. It's just the same 3 rules over and over again. Like, to me, it's not as complicated as the exponent rules, because the exponent rules can involve like 50 different letters at the same time, and then like 50 different rules at the same time. For these, there's really only the main 3. Can you combine them using addition? Product rule. Can you combine them using subtraction? Quotient rule. Can you take the coefficient out? Power rule. Those are the 3 things you're really going to be doing. So, cool. I think these are pretty straightforward. And they just take practice. You got to be able to see those things, right? Alright, we can also use these to solve a few logarithmic equations, some little ones. We can start right here. So I have log 3 of 6x plus 5 equals 2. Here I don't even need the rules. I don't even need the rules for this one. All I have to do is make my circle. Boop. I'm gonna... No... Okay. I'm just gonna up my width a little bit. Sorry. Picky. Okay. So here I just have to make my circle, right? And I just gotta go whoosh, like that. And that just means 3 squared equals 6x plus 5. Well, that's super easy because I know 3 squared. 9 equals 6x plus 5. Now it's a math problem from 8th grade. Fabulous, right? So it's not that these are going to take every single rule and every single hour and they have to be at the end because they're so complicated like chapter 9. No, these ones they're pretty straightforward. You just got to convert them first, see if you can convert them, and then solve. Subtract 5 from both sides, you get 4 equals 6x. And then divide by 6, you get 4 6 equals x. And if you reduce that, x equals 2/3. Ta-da! Super easy. Let's try another one. Okay, this one is a little trickier, right? Because I can't just draw my circle. I can't convert it back a little bit. But notice something. Notice something. You have log 10 on both sides. Maybe if I put them on one side, I can use my product rules, or my logarithm rules. So let's move this one over. But Miss K, there's nothing else on the other side. Yes, there is. There's always a 0, right? So you can move anything you want. 0 is always a good placeholder. This was 1 minus log 10 3 equals 0. Cool. I'm going to kind of forget about that log 0. I'm going to forget about the 0 thing on the other side for a minute. I'm going to quotient rule this. Log 10 of 6x plus 1 over 3 equals 0. Now I'm going to circle. 10 to the 0 equals 6x plus 1 over 3. What's anything to the 0 power? That's right, it's 1. Okay, I'm going to run out of room for this problem. So you know what I'm going to do? That's fine. I'll just go over here. So I have 1 equals 6x plus 1 over 3. Multiply that to the other side. You get 3 equals 6x plus 1. Subtract 2 equals 6x plus equals 6x. And you finally get that x equals 3. Yay! So this took a little bit longer because I actually had to use a rule this time, right? If you have 2 logs, you got to get it down to 1 so that you can convert it, okay? So take care of those first. If they happen to be on different sides, fix it. Move it over. No big whoop. No dealio. All right, cool. Like I said before, the spacing in this one got a little off. Yours is fixed, okay? But what I'm going to do is I'm going to use this space right here to do C and D, because on the next page I have plenty of room to do example 1. So, unfortunately, I can't cut and paste the text, but we'll just rewrite it later. So you just have to keep up with me. You guys are almost in college now, so you'll be fine. All right, so I'm kind of just going to like that. All right, I have log 5 of 3t plus 2 minus log 5 of t equals log 5 of 4. That's a lot of logs, but luckily, they're all log 5, right? They're all log 5. I don't have to worry about converting multiple things. This is going to be pretty easy. It's almost the same problem. I'm going to start, no, I'm not. I'm going to move all the logs to one side first and then use my rules. That is not always it's not always the best way, but it's kind of a good rule of thumb, right? It's get all the messy things to the same side so that you can do a simple problem as opposed to trying to do multiple problems, right? So log, I just want to save space here, so log 5 3t plus 2 minus log 5 of t, that I didn't change, but now I'm moving this guy over here, minus log 5 of 4 equals 0. Notice how it follows the same rules. When you subtract something, you subtract it to the other side, right? When you move something over that's positive, it now becomes negative. It's not any different because it's a log. All right, both of these are being subtracted. That means both of these apply to a quotient rule, so I end up with log 5 3t plus 2 over t times 4. Yes, it's times, even though they're both being subtracted, even though they're individual, right? If I pulled out that negative, they would be adding log 5t plus log 5 4, so that would mean it would be t times 4, or 4t, right? We could do 4t. That would be fine too. 4t. And that still equals 0. Alright, I got 1 log now. Make my circle. Thank you, Mr. Keller. 0 equals 3t plus 2 over 4t. Well, what is 5 to the 0? Yep, that's right. It's 1 equals 3t plus 2 over 4t. Multiply the 4t to the other side. You get 4t equals 3t plus 2. Subtract 3t. Don't panic. Just because you have t on both sides, you can fix that. You get t equals 2. Ta-da! Hooray! We did it! We took something that looked like a nightmarish problem up here, and we figured out t equals 2. Awesome. It didn't equal 3i plus 47 root 25 over 360p, you know. It equaled 2. So these can be done, okay? Don't give up. Don't give up. All right. Last one of these, we've got log 2x plus log 2x minus 7 equals 3. I see product rule straight off the bat. I don't even see something I have to move. This problem's probably not going to be that hard. Sweet. Log 2, I'm going to just try and zoom in so I can write a little better. Log 2 of x times x minus 7 equals 3. Okay. You're going to have to forgive my son crying in the background. Oh well. Okay. Cool. I'm already simplified with my log rules. Now I just have to make my circle. So I get 2 to the third is equal to, I'm actually going to multiply that out. X squared minus 7x. Okay. It's a quadratic. Don't panic. We're going to be fine. 2 to the third is 8. x squared minus 7x. Move the 8 to the other side. You've got 0 equals x squared minus 7x minus 8. Oh, sweet. It looks like this one's kind of going to factor, right? Because what two things multiply to negative 8 and add to negative 7? I'm thinking 8 and 1. I'm thinking 8 and 1. Negative 8 and 1, right? So we're going to get 0 equals, ooh, and even better, a is equal to 1. So I know this is just going to go to x minus 8 and x plus 1. And x plus 1. So x is going to equal 8 or x is going to equal negative 1. Fabulous! If you have no idea what I just did there in those last 3 steps, you need to go back and review chapter 6, factoring trinomials, okay? Factoring trinomials, specifically 6.2. 6.2 is that's where factoring trinomials is. You got to be solid with those guys. Either factoring, I mean, you could plug that into the quadratic equation, but you're looking at radicals again, and that's just such a waste of time. Notice I took 3 steps, right? Always double check. Did anything multiply to this and also add to that? Oh, hey, cool, yay. Okay, cool. All right, that's solving with equations. A lot of logarithmic rules that we have. We're going to graph one more thing. No, that's it for logarithmic rules, okay? But we're going to talk about one more thing in this chapter. We're going to talk about a little bit more about their graphs and how they transform, just because they kind of go along with the rules and what they do. So I'm going to switch colors here. Once again, I do apologize about my sort of mix-up here. What I've scratched out here, it says in example 1, come on, work with me. There we go. So in example 1, we're just going to draw the graph. Draw the graph of, what was it? Y equals log 5x. Y equals log 5 of x. Alright, so remember back from the last section, logarithmic functions are inverses of exponentials. So it's going to be easier to graph this as an exponential than it is as a logarithm. So let's go ahead and we'll have to circle backwards, but we'll make our circle. 5 to the y equals x. So we'll make our little table. Choose 1, 0, and negative 1. Remember, I'm choosing y, not x, because y is going to be easier to plug into. There's no legal rule that says you have to choose x. 90% of the time it's easier to choose x. In this case, it's not. So why don't we just choose y? Let's just choose y. 5 to the first would be 5. 5 to the 0 would be 1. And 5 to the x would be, whoops. What would it be? 1/5. Okay, I have 3 points now. 5, 1, 1, 0, and 1/5, negative 1. So I'm going to draw myself some axes. Okay, cool. Next up, I'm going to plot these points. Out 1, 2, 3, 4, 5, up 1, out 1, up nothing, and out up 1/5, and then down. Okay, now I know the second one goes up to 25, so I'm just going to kind of keep it within there. And then I also know the asymptote of this is the y-axis. It's not going to cross over the y-axis. It's going to get really, really close to the y-axis. So I'm kind of just going to skim along that. And we've graphed y equals log 5 of x. Why did we do that? I'll talk about that in just a sec. But that was kind of a review of how to draw the log of draw a logarithmic graph. This is what we call a parent function or a parent equation. In this case, it is a function, so we're going to call it a parent function, which just means exactly what you think it means. It's the older brother. It's the original, right? When you transform it, though, you don't really call them children functions, but that's essentially what they are. You get more of like you get a different graph, but it's clearly similar or made from the first graph, okay? So parent function is usually the ones that don't have any crazy things going on with x, okay? We don't see x plus 5, we don't see x minus 2, we don't see a coefficient in front, you don't see anything like that. So the log 3 of x, log 4 of x, log 5 of x, even log 1/2 of x, log 1/6 of x, the base doesn't really matter. It's where the parent function just doesn't have anything on the outside. It doesn't have a coefficient and doesn't have anything happening to x. So these are our parent functions. But we can change that. We can definitely change that. Let's take a look down here. Some transformations. If it doesn't have a transformation, it's just called a parent function. That's what this is, right? But we can do all sorts of things. We're going to focus on 4 main ones. If you throw on an additional letter, or sorry, an additional number, if instead of just of x, you have x plus k, as it's shown here, what that's going to do is it's going to shift it 1 to the left. Similarly, if you have x minus something, it's going to shift it to the right. Now you gotta be careful with that one, because you would think the left side's negative. So if I subtract, I'm going to go to the left, but that's not true. If you add it, it pushes all the numbers back. Okay, I know that sounds really weird, but that's exactly what it does. It pushes everything back, as opposed to pulling it to the left. So plus is left, minus is right. If they are not part of the argument, if they're just tacked on the end, so it's not log a of this x plus 2, it's just log x, and then also adding another number like plus 2, then what's going to do is it's going to move up and down. You may recall that back from secondary 1. It happens with everything. So these are the same 4 transformations no matter what. If it's inside the parentheses, you're going left and right. If it's outside the parentheses, you're going to go up or down. Okay, so let's take a look at these. We're going to take a look at one of each, and then we'll be done with the rules of exponents. Okay. I'm sorry, the rules of logarithms. Okay, so we're going to draw ourselves some axes. Okay, now I'm going to spend a little more time on this first one than I am the other 3, because there's a really fast way to graph these, and there's ways to really see why this is a transformation of a parent function. Okay, so we're going to start by graphing this just as it's given. Okay, so we're going to pretend we're just sitting there, right? It's a graph. We're just going to do the same thing we did for all the other ones. So first we have y equals, we have this, so we're going to make our loop. We're going to go this way. We have 3 to the y equals x minus 5. Right? That's our function, right? That's our transformation. That's how we converted it to an exponential. So let's make our table. We have x and y. We're again going to choose the y's, because that's going to be a lot easier than trying to choose the x's and finding the exponents, right? It's hard to find exponents. So we're going to use the exponents. We're going to choose 1, 0, 1. Or negative 1. I'm even going to choose negative 2 and 2 as well, because I want to really see what this looks like. Alright, so I plug in 1, I get 3 to the first equals x minus 5. 3 to the first equals x minus 5. Well, 3 to the first is just 3. So what minus 5 would be equal to 3? That would be 8. Alright, next up we plug in 0. 1 is our answer on that side. Add 5 to it, you get 6. See that? You get 6. Negative 1, you plug in negative 1, you get 1/3. This one's a little harder. X minus 5. We're going to add 5 to that. We get, let's see, 16/3. So x is equal to 16/3. You don't trust me, use a calculator. Plug that in. Plug in x to the second, we get 1/9. I'm sorry, negative 2. X minus 5. Add that to the other side. 5 would be 45/9, so this would be 46/9. And then 2, positive 2, that's nice and easy. You get 9, so x must be 16, right? We add 5 to the other side. I'm sorry, 14. You're going to get 14. 14, so that's that one. Okay, so we have our 5 points now. Let's go ahead and graph that, right? We have 8, 1. So 1, 2, 3, 4, 5, 6, 7, 8, up 1. 6, 0. 1, 2, 3, 4, 5, 6. And then negative, it would be 16 thirds. What's that? 16 thirds. 15 thirds is 5, so 5.33333, right? So 5.33333 down 1. And then 46 over 9 would be 5.11111. That's like right there. And then we have 14, which is going off the page. So looks like our function's looking kind of like that. All right. Doable. Definitely okay. We can figure it out. It's a lot of math, right? We have to solve a little mini equation every single time, but we can do it. The second way to do this is to really treat it as a transformation. Why is this a transformation? Well, let's look at the parent function. Let's look at y log 3 of just x. Okay, so this is the parent function. Log 3 of just x. Okay, just x. If we do that, well, then we end up with, here's my x and y, right? 1, 0, negative 1, 3, 1, and 1/3. If you don't trust me, go back and look at the other videos. We've done this one probably twice now. We're going to plot that on the same graph. Let's see. We had 3, 1, 0 there, and then it went down like that, right? Next one was 9, and then I think the next one's 27, so it went like that. And then, of course, it kind of skims the y-axis. All right, so that's our parent function. Compare those two. How is the pink one related to the red one? Looking specifically here, let's track it. Let's track that. So if I look right here, then from 1 to 6, how far over did that go? That went right. That went to the right. To the right 5 spaces. That's exactly what it did. It went right 5. That's what it did. From the parent function, from the original, from the beginning, it went right 5. And if we look here, isn't that what it said it would do? Right? Isn't that what the table said? When you subtract a number, you go right that many. Here we're subtracting 5. So it went 5 to the right. So what I could do, instead of having to do all these little mini equations, instead I could just plot the parent function, maybe in one color, and then I could pick a few dots that make sense to me, and maybe the ones I chose for my graph, right? And just move them all over 5. That's going to be so much easier and so much quicker than trying to do this little mini equation every single time. And maybe, as long as I indicate to my teacher or whoever's grading my paper, this one, I mean this one, that's right 5. Like maybe erase the parent function afterwards. But that's all you have to do. It's a transformation 5 to the right. Cool. Alright, like I said, I'm going to spend more time on that one than any other ones. Let's just use these other ones and let's just graph these other ones using their parent functions, okay? So what is the parent function here? The parent function would be not y equals log 4 of x plus 2, but just y equals log 4 of x, right? So we're just going to use the basic, the original. So let's just graph y equals log 4 of x to start with, okay? So we have our x and our y. We choose 1, 0, negative 1. Again, you can technically choose whatever you want, but you got to choose both sides, or you're not going to choose both. You're not going to get both. All right, log 4. Let's see. Convert this. You get, I'm sorry, this way. 4y equals x, so 4 to the first equals 4, 4 to the 0 equals 1, 4 to the negative first equals 1/4. Cool, I have enough information to graph this now. Oops. Oh, crud. Okay, good enough. That was much better. Okay, so I have 4, 1, 0, 1, 0, and then 1/4. And then the next one would be 16, so it goes off the page. Again, sorry about that. Okay. And skims the y-axis. The parent functions will always skim the y-axis. Always skim the y-axis because they're parent functions. Nothing weird is happening to them, right? Okay, cool. That's the parent function. Now, according to this, how is ours different? What transformation has been applied here? Let's see. Plus 2, that means it's going to be pushed backwards 2. So it's going to go left 2, right? It's going to go left 2. That's what that says. So when you add a number inside the parentheses, you're going to go backwards. So I'm going to choose a different color, maybe green. And then these points that we made, I'm going to go back 2 from them. So rather than being on 4, 1, I'm going to be on 2, 1. Rather than being on 0, 1, I'm going to be, or 1, 0, pardon me, I'm going to be on negative 1, 0. Rather than being 1/4, I'm going to be over here. Right, so I'm going back 2. And then we connect the dots. 16 going back 2 would be 12, so that's still off the page. I'm sorry, it would be 14. So let's go back there, kind of skim there. And then we're going to skim on negative 2 as opposed to on the y-axis where x is 0. And we did it. You're like, Miss K, that doesn't look like everything went back 2. I know. Sometimes that overlap, you kind of think, well, did I do that right? Is it really back 2? I mean, some places don't look the same. But if you analyze it dot by dot, you're going to find that a lot of them, that they are all back 2. Yeah. Okay, cool. Let's try one that is not a left or right. What's happening in this one? Well, notice it's outside the parentheses. It's actually saying do this and then add 6 to it, which is exactly what we're going to do, right? We're going to plot the parent function, log 2x, and then we're going to add 6. It's going to be super easy. So I'm going to use this space here, x and y. The parent function is just log 2x, or 2 to the y equals x, so I'm going to choose 1, 0, and negative 1. That would be 2, 1, and 1/2. Right? 2 to the first is 2, 2 to the 0 is 1, and 2 to the negative 1 is 1/2. Alrighty, and I'm going to plot myself some axes. Good enough? Okay. 2, 1 was the first point, 1, 0, 1/2. Now this one I actually might be able to squeeze in a couple more, because if I go by my squares, it's going to be, there's a lot going to be on here, like 2 squared is 4. That's 2, here's 4. 2 to the third is 8. 4 more. And then we've got 2 to the fourth, which is 16, and that's off the page. So I can fit a lot more dots in here. Do you need to put all these in here? No. But your arc should go up to about the 4th one, right? It goes all the way to 4 before it goes off the page. If you just go like this, then that's kind of just lazy. So you don't want to do that. Plus, if you're trying to plot points and move them over or up and down, you're going to get the wrong picture, right? So maybe plot a few more if you know it's like really small, right? Or just always check squared. I don't know. Do whichever you want, but make sure it looks fairly accurate. Accuracy is good. Okay. Now, what is it telling me this transformation is? We kind of already talked about that. It tells me do the parent function and then go up 6, right? Add 6 to each of these points in the vertical direction. If it was minus 6, we'd be going down 6, but it's not. It's add 6, so we're going to go up 6. So from here, it's a good place to start. 1, 2, 3, 4, 5, 6, up. From here, 1, 2, 3, 4, 5, 6. From here, 1, 2, 3, 4, 5, 6. Here, 1, 2, 3, 4, 5, 6. And notice, actually I'm going to use a different color because this is not the same line. We get this, the same kind of curve, the exact same kind of curve, the same speed at which it grows, and the same asymptote here, but it is now 6 up. That's all that's happened, right? Alright, cool. Last but not least, we're going to apply multiple transformations. So what does this one say? Well, it's hard to read because I wrote over it. Boop, there we go. It says, take the parent function and do what? Well, what's the parent function? The parent function, is it log 2x minus 3, and then I have to add 4 to it? Is it log 2x plus 4, and then I subtract 3? It's both. It's neither, actually. It's just log 2x. It's always a parent function, no matter what you do with it. It's the ones that's weird, or that's basic. It's not weird in any way. There's no minus 3, no plus 4. So the parent function here is just log 2x, And if you want, you can put the y on the other side, right? Because then it's easy to draw your circle. So there's log 2x, that's it. So we have 2 to the y equals x. Well, that's super easy. We just did that one, right? So we can do the same xy. Again, it's easier to choose y, not x. So I'm going to choose y. And I end up getting 2, 1, and 1/2, just like we did a moment ago. I'm going to go ahead and plot those. First I need axes, and I'm going to draw a heck of a better line than that. And then this way. There we go. Okay. So I have 2, 1, 1, 0, and 1/2. And then as we saw before, I can also do 4, 2, and then 1, 2, 3, 4, and then 8, 3, and I have my parent function. I wouldn't worry too much about the halves. It's all going to skim the y-axis anyway, so that's fine. But if for the side there, the positive versions, you do kind of want to be accurate. All right, now, do I have to draw 2 more? Do I need to draw 1 for each? Not really. If I look at what transformation is being happened here, I can apply all of them at the same time. Okay, I only care about the end goal here. The parent function just lets me see where I'm starting. If you want to make sure you're super accurate, yeah, you could do -3 to the right 3, right? Because a -3 in the parenthesis means right 3. And then you could go up 4. But why don't you just do both at the same time? Why don't I just move every dot 3 to the right and up 4, like counting slope? It's really not that hard, right? So let's choose a different color. Let's do purple. We're going to take this dot and move it 1, 2, 3, up 1, 2, 3, 4. That's where that one went. 1, 2, 3, up 1, 2, 3, 4. That's where that one went. 1, 2, 3, and up 1, 2, 3, 4. That's where that one went. Another thing, if you want to save some time, you can say, okay, well this one's right there, and this is supposed to be one diagonal from it. I'll just go one diagonal here too, right? That's legal. The movement of the curve should not change the curve. Like if you look back at our last problem, like we said, we get the same curve. It's just 6 inches higher, right? So if you wanted to do it that way, you can. You just have to be much more careful about how you move your dots, right? About how you connect your dots. So this one goes over 1, 2, 3, up 1, 2, 3, 4. And then this is going to be, that was this one, so 1, 2, 3, up 1, 2, 3, 4. For example, this last dot I just drew, right? Just because it's moving over 3 and up 4 doesn't mean it's suddenly going to be on one of those vertical lines, right? It's currently sitting at a halfway point. Moving it 3 over is going to move it to 3.5, right? Not 4. So I got to be accurate about this. I have to make sure if I'm moving the half point over, it's got to stay half over. And then we go down. So this y-axis, this asymptote's changed, right? It's moved 3 over. The whole asymptote itself has moved 3 over. And there is my actual function. So this is my transformed function. Maybe I draw an arrow to it. Maybe I grab my pencil and I erase the parent function to indicate that this was in fact the one that I wanted. I wouldn't erase the work. Okay, I wouldn't erase anything we did over here because just in case you make a mistake, Miss K, on the test, I can, give you a few partial credit points, but maybe if you wanted to erase it or grab some colored pencils, you guys know I have colored pencils in my room, you can more than welcome to color it and say, it's the purple one. Okay, cool. Alright, so we've talked a lot today. Talked a lot about rules of logarithms, right? There's the 3 big ones, the product rule, the quotient rule, and the power rule. How they can be used to solve equations, and then how you can graph transformations using these shifts. Awesome. The next section, 10.4, will close out the chapter. It's about common logs and natural logs. You guys are going to love it. It's all about calculators, but at the end of the day, a logarithm is just an inverse of an exponential function. See ya.